All right, so we're going to continue on talking about, or not talking about, but understanding our use of the fundamental theorem of algebra, and specifically we're going to be focusing on the complex zeros and what we want to notice about them. So let's jump right into it. For both A and B here, I want you to find all of the zeros of each polynomial. Now, I'll give you a hint. I've already graphed a part of each polynomial for you, and that should help you find one of the zeros. So think about what we did in the last video, how once we used our calculator and found a zero, what did we do from there? So I want you to go ahead and do that. Pause the video, find all the zeros, unpause when you are ready to discuss. Okay, so on the left here, I got x equals plus or minus 2i. And remember, this is two separate answers. So this is 2i and negative 2i. And I got x equals 3. On the right, I got x equals negative 5, and I got x equals I root 3 and negative I root 3. Now, I did these problems two different ways just to show you and make sure we're understanding that there are many ways to do these problems. So the one on the left, I used my hint that I told you before we paused the video and did our own work, and I recognized, okay, I see that there's a 0 at x equals 3, so from the previous problems we've done, I did synthetic division with 3. So I set up my synthetic division. Here are my coefficients, 1, negative 3, 4, negative 12. Did my synthetic division process. It worked out, and I know that because I got 0 as a remainder. So that's good. Now, what was I left over with? X squared plus 4. Set that equal to 0 to continue to find the zeros. Subtract 4. I get x squared equals negative 4. Take the square root of both sides. Remember, the square root of negative 4 is, well, the square root of negative 1 is I, the square root of 4 is 2, so I get x equals plus or minus 2i. Now, don't forget, 3 was also a 0, right? So when we're listing all of the zeros, I should have 3 total zeros because the degree was 3. And so I include x equals 3, and then plus 2i and minus 2i. Now, over here, I could have done the same thing and recognized that negative 5 is 0 right here. Let's use a different color. Right? So I can see that. Or what I chose to do here is just factor by grouping. And now I want to point out, I could have factored this one by grouping also. So again, I'm just showing you different methods. It's up to you what you prefer to do. Now remember, not everything is going to factor by grouping though. But this one did, so that's what I did. So first I set the equation equal to 0. I group the first two, group the second two, take out my GCF from the first two factors, and that was x squared. Take out the GCF from the second two factors, and that was 3. Now, as we talked about before with the factoring by grouping, I know that this worked because what was left over in the parentheses was the same thing for both of them, and that is x plus 5. So that means that it worked, and I did this correctly. So then I factor out the x plus 5, and I'm left over with x squared plus 3. Because this equals 0, I can set each of my factors equal to 0. I get x equals negative 5, and then here I get x squared equals negative 3, take the square root, and that's how I end up with x equals plus or minus I root 3. Or again, remember this is actually two separate answers. It is I root 3 and negative I root 3. Now, also just pointing out, the negative 5, right? We talked about that. I knew that was going to be one of my zeros. So it's a good thing that I got it as one of my zeros. And again, I have a total of 3 zeros. Okay, so what we're actually getting to is not only just being able to find zeros, but recognizing a pattern. So do you notice anything about the imaginary zeros specifically from the last two examples, as well as really every single example we've ever done where we ended up with imaginary zeros? So I want you to pause the video and actually think about this for a couple seconds and see if you notice anything. All right, so what we hopefully notice is that anytime we get complex zeros or imaginary zeros, they always come in conjugate pairs. And that should make sense because anytime we're solving for them, we are taking the square root and doing plus or minus, which is creating the conjugate pairs. So this is not a coincidence. This is a theorem, the complex conjugate theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary zero of f, then a minus bi is also a zero of f. All right, so now we are just formally stating that. Similar to when we had the conjugate irrational root theorem, this helps us when we are actually trying to write polynomials. So, for example, if I want to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 2 and 3 plus I would follow the same pattern I did for those problems with irrational roots, where I would say, okay, if my zeros are x equals 2 and x equals 3 plus I, then I know if I'm going to have rational coefficients and it's going to be a polynomial, then I also have to have a zero of 3 minus I. So then I can write my factors, x minus 2, x minus 3 minus I, and x minus 3 plus I. Whoops, we want f, so I'll use f. So then my polynomial f of x is x minus 2 times x minus 3 minus I times x minus 3 plus I. Again, just reiterating conjugate, the middle term is the one that changes sign. The first term does not. Now, also keep in mind that the complex number needs to be in standard form, which is where the real part, a, is first and the imaginary part, bi, is second. That's how we write the conjugate. Okay, so I want you to try this for all of these. So there are 4 problems here. And all you're doing is exactly what we did on the last example. Write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. So here, negative 1 and 4i, 3 and 1 plus I root 5, root 2 and 1 minus 3i, 2, 2i, 4 minus root 6. So do that for all of those. Pause the video. Unpause when you're ready to discuss. All right, so what did we end up with? Great question, glad you asked. So here, if we're given x equals negative 1 and x equals 4i, then I know x equals negative 4i also has to be a 0. So my factors are x plus 1, x minus 4i, and x plus 4i, so this is my polynomial. Here I'm given 3 and 1 plus I root 5. So x equals 3, x equals 1 plus I root 5, therefore x also has to equal 1 minus I root 5. So my factors are x minus 3, x minus 1 minus I root 5, x minus 1 plus I root 5. Here, I'm given x equals root 2, so that means x equals negative 2 root 2 also has to be a 0. And here I'm given x equals 1 minus 3i, so x equals 1 plus 3i also has to be a 0. So when I write these as factors, I get x minus root 2, x plus root 2, x minus 1 plus 3i, x minus 1 minus 3i. The last one, now we just have 5, so we're given x equals 2, x equals 2i, so x equals negative 2i has to be a 0. X equals 4 minus root 6, so x equals 4 plus root 6 has to be a 0. Now I write these as factors, x minus 2, x minus 2i, x plus 2i, x minus 4 plus root 6, x minus 4 minus root 6. Boom. All right, big takeaway. What is it? Complex zeros come in conjugate pairs. Nice work.